Okay. Okay, so let's look at direct proof now. So direct proof is usually a proof method that we want to prove something of this form. P implies Q. We want to prove something of this form. P implies Q. So I'll give you an example of what is the thing that we want to prove for P implies Q. Something like if n is an odd integer, then n squared is also an odd integer. Okay. Now, suppose that this is the theorem that we want to prove. And then, if you look at the format of this theorem, it is like P implies Q, right? And then to prove that this theorem is correct, what do we need to do? We may just focus on the case that this part is true and see if this part is really true, then whether the next part is also true. Because to prove P implies Q, if I tell you that P is already false, you don't need to do anything. Right? Because false implies anything will be true. Okay. To just make sure that this theorem is correct, we may assume what? So the strategy is very simple. We assume P to be true. And after some steps, after some reasoning, we get Q as a conclusion. Then this is done. So this is the strategy. So this is why it is called direct proof, because we directly assume that this part, the P part, is true already. And then we go on to conclude that Q is true afterwards. Okay? Now just as this very simple example, so we still need to do something. Okay, so using this structure, this is the structure, the form. This is the form that we are going to use. So we can do this. So we first assume what? Assume n is odd. This is what n is an odd integer. So what immediately can we conclude? So if n is an odd integer, so what is meant by an odd integer? What is meant by an odd integer? N is odd. What is meant by odd? 1, 3, 5. Okay, you know it is odd. But what is some property that every odd integer has? Okay, so it is like, it is always 2 times a certain integer plus 1. Am I correct? Okay. So from this one, we get this as an immediate conclusion. Then n is equal to 2k plus 1 for some integer k. Is that okay? So this is saying there exists some integer k such that n is equal to 2k plus 1. Okay. But we are writing something in human, understandable language. We are not writing something like there exists k such that what? K is an integer, something like this, and n is equal to 2k plus 1. Okay. Of course, you can write down something like this. They are equivalent. But then inside the proof, we usually write it down because it is for human to understand rather than for a computer to check. Okay, so it is good enough to write down something like this. Okay, then what do we have? We have this one already, right? The next one is we hope to arrive at this conclusion Q is true. So Q is about n squared is odd, right? It's about n squared. So let us now look at n squared. So if n is equal to 2k plus 1, so, these are your choice. You can use then, so, therefore, whatever. So make it readable. Okay. So n squared will be equal to what? It will be equal to 2k plus 1 squared. Is that okay? Okay. And now the best way to expand this is equal to, this is 4k squared plus 4k plus 1. Is that okay? Okay, now we are nearly done. Okay, nearly done. If we can somehow show that this is an odd integer, then it's done. How do we show that this is an odd integer? Okay, of course you can use properties of integers. This is even. Even times any integer is even. Even times any integer is even. 1 is odd. Even plus odd is equal to odd. Okay, so you can write down like this. Or you can also try to make this in a form that an odd integer looks like. So if you can find that this is equal to 2 times some integer plus 1, then that will be great. So this is perfect here. So this is 2 times 2k squared plus 2k plus 1. Is that okay? And then just to make sure that the one who is reading your proof understand what you are talking about, so you may quote it as this part is an integer. Right? So in that case, at this point, we have shown that n squared is equal to 2 times an integer plus 1. So it is odd. So n squared is odd, we get the conclusion. Is that okay? So this is about direct proof. Direct proof is nothing special. Usually, direct proof is something like you have something assumed. If something happened, then something happened. Then the proof strategy is you take it for granted. You use this, and then as a result. And then hope that you can get the conclusion afterwards. Okay? Okay? Good. Okay. Okay, so let's now take a look at another example. Also direct proof. So here, let's write down if. So we prove another theorem. So if this time m and n are both perfect square, then m times n. So this is m times m together is also a square. Number. Okay, so for this one, this is also a very easy example. So we try to prove it, so we write down, okay, proof. So the following is the part that contains the proof. So we assume this one is correct. So we copy this again. Okay, I'm just being lazy. Okay. So assume that m and n are both square numbers. So this is something that I missed. So I'm copying this sentence here. Then what do we have? Then what do we have? Then what do we have? If m and n are square number, what does it mean? What is meant by a square number? 1 is a square, 4 is a square, 16 is a square, right? A square number is equal to the same number multiplying itself. Okay? Then you can write down m is equal to some number multiplying itself. So you give it a variable. Let's call it s, whatever. M is equal to s squared. N is equal to t squared. I don't know which s, which t we take, but I know that because I know that some of them exist for some s and t. Is that okay? So make it more specific. For some integer, so we need integer. Okay. S and t. Okay. This is what we can conclude so far. After the assumption that m and n are both square number, we can now, so we have this assumption there. So m and n are already square number. We assume this is true. So we can next talk about, okay, because it is a square number, so m must be equal to some s square. And then n must be equal to some t square for some s and t. Is that okay? Okay. Then what do we have? So now, take a look of m times n. M times N will be equal to S squared times T squared, right? And then how can we conclude that it is a square number? So this is, we just rearrange it into a beautiful form. This is S times T whole square. Is that okay? Okay, then done. So thus M N is a square number. Okay, and then this is the end of the proof. So this is the end of the proof. Nothing else we need to. So very simple. Usually, if it is a direct proof, usually it is simple. You take every part in the if part as what you can use, and then use that fully, and then you can arrive at a conclusion. Okay? But sometimes, direct proof is not that powerful. Take a look of this one. So here, let me write down. So n, suppose that n is an integer. I don't know, but it is an integer we are talking about. Suppose that n is an integer. And then we are saying that if 3n plus 2 is odd, then n is odd. Okay. Now it looks like this is still, so this is still an argument that is of the form P implies Q. This is P part, right? This is P part. I'm just adding one more thing. This is not that relevant, so I can put this here, okay? If 3n plus 2 is odd and n is an integer, then n is odd. So this is what I'm saying. And let's see what happens if we try to prove it using the direct proof. See if it works. Okay, so proof, okay, so the proof we tried, I don't know whether it works, so I put a question mark here. So assume that, we can assume 3n plus 2 is odd. Then what can we conclude? Then, of course, you can write down something like 3n plus 2 is equal to 2k plus 1 for some k. Okay, this is what we can do because we just assume that 3n plus 2 is odd. So in that case, 3n plus 2 is equal to 2k plus 1 for some integer k. But then what? But then we have what? Okay, let's still use algebra to do this. This is minus. So we will have something like a very strange one. N is equal to what? N is equal to 2k minus 1 divided by 3. Right? I'm using algebra, so put a 2 over there, so 2k minus 1 divided by 3. And then, from this one, there is no way that we can conclude n is odd. I tell you that n is equal to 2k minus 1 over 3. So n can well be a fraction. It doesn't look like this is an integer, right? If you tell your friend that this is an integer, then they will tell you that you must be wrong. You must be wrong. Okay? So in that case, the direct proof in this example fails. So somehow, this is still something that we can understand. Yes. What else can n be? If n is not odd, n will be even, right? But if n is even, then 3n plus 2 will be even. Then this is not okay. So using our own experience, we will know that this is something that is true, but we cannot use direct proof to prove it. So now we use the strategy of indirect proof. So in direct proof, there are two different ways. One is proof by contraposition. Contraposition is we try to prove P implies Q. This is something that we try to prove. But then we use the equivalence. So we know that instead of proving P implies Q, we can prove something like not Q implies not P. Is that okay? Okay. The reason is that P implies Q and not P implies not Q, they are logically equivalent. They are the same. If I can show that this is always true, then I can show that this is always true. This is what we try to do. How about contradiction? So I hope you still remember what is meant by contradiction. Contradiction is a special word in logic. What does that mean? Always false. Okay. So always true is called a tautology. Always false is called a contradiction. Okay. So proof by contradiction is something like, if I want to prove a certain statement Q, then I'm not proving Q directly. I will show that not Q implies false. Okay? This is what they are equivalent. Okay? They're equivalent. Okay? They're equivalent. So to prove that Q is always true, you need not Q implies F is always true. Because if Q can be false, then this part you will have true implies false. Then you will have something false here. This is not okay. So to prove that this is always true, it is the same as if we are proving this is always true. So this gives us two different ways of proving the same thing. We do not prove the original statement, but instead we prove a different version of the theorem of the statement. Okay, just as this example, let us use proof by contraposition to do that. So contraposition, we know that this is what? So we have another proof. So first of all, what is the contraposition? The contraposition is if n is not odd, then 3n plus 2 is not odd. Okay? So these two are exactly the same. This is in the form of P implies Q. This is in the form of not Q implies not P. Okay? Okay? Now, so the proof, instead of proving this, we directly prove this. And then this is of the form of something implies something. We use direct proof of this part. Is that okay? Direct proof of the, we call it the contraposition. So the proof is assume n is not odd. Okay, n is not odd, but then since n is an integer, so we assume that n is always an integer to talk about in both cases. This implies what? N is not odd, n is an integer, so it must be even. Very good. Very good. N is even. Okay? N is even. Okay, n is even. So n is equal to 2k for some integer k. So we can find some integer k such that n is equal to 2k. Okay, then 3n plus 2 will be equal to 3 times 2k plus 2. Is that okay? 6k plus 2. So this is equal to 2 times 3k plus 1. Is that okay? And then k is an integer. So this part is also an integer. Okay, k is an integer. 3k is an integer. 3k plus 1 is an integer. So this is not odd. And done. This is it. So we can stop it here. Because we have finally concluded that 3n plus 2 is not odd. This is what we want to do. Is that okay? So this is called a proof by contraposition. Okay. So this is the This one is the contraposition of this one. This one is the contraposition of this one. Okay? So today is Monday, right? On Wednesday, let us continue to prove something even more interesting. So using this, actually this kind of indirect proof, it is in the history for a very, very long time, probably, so at least 2,000 years, at least. So by the time of Euclid, we already know a lot of results that requires this kind of proof by contradiction to use. Okay, so this kind of logic has been there for many, many years, at least 2,000 or nearly 3,000 years maybe. Okay, so let's end the class early today. Okay, thanks a lot.